Okay, so let's a little bit about bond energies. Bond energies, we talk about a lot of that in terms of enthalpy. Remember, enthalpy is bond energy. And so we either have in a reaction a net gain or loss of energy. That's where we get our endo and exothermic reactions from. But if we say a compound has 300 kilojoules of bond energy or enthalpy, where does that come from? Well, it comes from the individual bonds between each of the two atoms in that particular compound. And so let's use two magnets as an example. And magnets, if in order to pull those magnets apart, we have to put energy in. It requires effort. So that would be considered an endothermic reaction. Whenever two magnets are, whenever new bonds are formed, that's when we release energy. Exothermic reaction. So when chemical reactions happen, we are breaking some bonds between atoms, we're forming new bonds, and whether that net gain of energy that's lost or absorbed determines whether we have an endo or exothermic reaction. So let's go ahead and do one here. I'm going to go ahead and show each of the bonds between. Oops, that's a hydrogen. So we have CH4. CH4 is methane. It's the primary component in natural gas. Plus oxygen. I'm going to show each of the bonds because it matters for the bond energy whether we have a single, double, or triple. So if we have a single bond versus a double bond, which would have more energy? Well, if it's between the two atoms, then the double bond has more energy, and obviously the triple bond has more, and that makes sense conceptually. Anytime you burn an organic compound, it always produces carbon dioxide and water. Let's go ahead and make sure this is balanced. We have one carbon on the left, one on the right. We need a couple water molecules to balance out our hydrogen because we got 4 on each side. And then let's go ahead and balance our oxygen. So we're going to have 2 there. All right, so then we're going to go ahead and calculate the bond energy between each of the atoms. So let's do our carbon to hydrogen bonds. Now we have 4 of those carbon to hydrogen bonds. And if we look at our table up here, each of those bonds has 413 kilojoules of energy in it. And then let's move on to our oxygen double bond. We have 2 of those. And we'll go ahead and place our values in there. 498. And then let's do our carbon to oxygen bonds. We have 2 of those. And our carbon to oxygen double bonds. 805. Quite a bit of energy, and that makes sense, right? It's a double bond. And then we actually have 4 oxygen and hydrogen bonds, right? Because we have 2 water molecules. So we have 4 of these, oxygen to hydrogen. If we look at our table up in there, 464. Okay, so we just calculate, then we can go ahead, next step, we can go ahead and multiply each of these out. So I'm going to go ahead and multiply them out, and then they'll appear. Okay, so I just went ahead and simplified ours. So here is the entire bond energy for CH4. Here's the entire bond energy for the 2 oxygen molecules. 1610 is for the carbon dioxide molecule. 1876 is for the water molecules. And so here's what's happening in this particular reaction. What we're doing is we are breaking these bonds. 1, 2, 3, 4. We got to break those. We got to put energy in, right? Okay. Those are endothermic reactions. Here's another endothermic reaction. We got to break 2 of those. Okay. Now, next we have some exothermic reactions. We have some forming of new bonds. So we have new bonds being formed. Remember, those are exothermic reactions. Those release energy. Whenever those two carbon and oxygen molecules come together, it releases energy. Then we release more energy in those exothermic reactions. So here's what's happening. Okay, we're going to go ahead and simplify here. When all is said and done, we have this amount of energy on the left side here. Okay, so when all is said and done here, we have 2,648 kilojoules of energy that we had to put in to break the bonds. Okay, so we had to put that much energy in to break the bonds first. Then, when all's said and done, we released in an exothermic reaction, we form new bonds. Okay, and you remember any time we have exothermic reactions that they're negative value, right? So here's one way of doing this. These are all negative because they're exothermic, they're forming new bonds. So what is the difference? Okay, now we can do this another way. Ready? We're going to go ahead, instead of just assigning a negative value, I just kind of wanted to make that point to you. Remember in our enthalpy diagram? Okay, what would this particular one be? An endo or exothermic reaction? Exo. So here's what we've got. Here's our products starting here. Okay, here is our reactants starting here. So here's what we're going to do. Ready? We are going to go ahead and find the delta H. Remember? Products minus reactants. Okay, let's do it this way. Because these are exothermic reactions, those are negative. So now what we're going to do is we're going to combine the two. Negative 3486 was how much energy was released in the forming of new bonds. 2648. 2648 is the energy required to break bonds. How much energy we had to put into it, right? 2648. When we add those two together, that's going to give us the net loss or gain. Okay, negative 3486 and 2648, sorry, that's supposed to be a 4 there, gives us a negative 838 kilojoules per mole of energy. And that right there shows it's an exothermic reaction. We gave off more heat than we took in, which matches our graph up here. Okay, so it's quite a few steps, a little complicated. You're going to do one of these. That's it. Okay, and it's going to be very similar to what I just did. All right, so that's where the energy comes from. It comes from the energy of each of the individual bonds. Good luck.